2018, number 5, part B, NILA's way. Because NILA's way is great. I think it made a lot more sense than the solution did. Plus shows that, she didn't just get that from the solution. She figured this out on her own, came up with a unique way to do it. So it's really stellar. Good job on this, NILA. So no matter how you do it, you have to know that dy dx is equal to dy d theta over dx d theta. No matter how you do it, you need to get that or know that. So, and also both methods started with knowing that x equals r cosine theta and y equals r sine theta. And, let's remember that our function was r equals 3 plus 2 cosine theta. All right, so what NILA did that I thought was clever is she said, instead of trying to do this derivative with the r still in it, we know we want d theta, right? We want everything in terms of theta. Our given value was theta. So let's get that r out of there because we have an expression for r. We have r equals 3 plus 2 cosine theta. So let's just sub that in for the r's here. And I think it makes the problem much clearer and much easier. So then for our r, we're going to substitute 3 plus 2 cosine theta. And then we have the cosine theta. And then for y equals r sine theta, we have our r is again going to be 3 plus cosine theta. And then it's going to be times sine theta. And then she just distributes everything out and does the derivatives that way. And it's, I think, much easier because you eliminate a variable right at the beginning. All right, so when we do this one, we're going to distribute. So she simplified these basically. So you have 3 cosine theta. You're going to have here 2 cosine squared theta. NILA right away wrote it as cosine of theta squared because she knows she's going to take a derivative, and that's an easier way to work with it. So that was good. I'll just change it later. And then for this one, we're going to distribute 3 sine theta, and then we have plus 2 cosine theta sine theta. Now, when you go to do the derivative of this one, you would have to use a product rule unless you're NILA and you were not only good at calculus, you were also really paying attention in pre-calculus and you remember all the identities, and especially the double angle identity, that 2 cosine theta sine theta is equal to sine of 2 theta. There was also, I forget which one it was, there was a book problem. It was one of the Taylor series one where if you had to use this simplification to avoid having a really big exploding product rule situation. So that was a really clever observation that she made. All right, and then so we have 3 sine of theta plus that sine of 2 theta. All right, we can't really combine those, but that's what it is. All right, so now if we look at the fact that we have x equals, I'm just going to rewrite these a little bit just for clarity. X equals 3 cosine theta plus 2 cosine of theta squared. So now I'm going to write that cosine squared theta like this so that I can do the derivative. Then I can get dx d theta. And then we just do a derivative normally. It's negative 3 sine theta. And then this is going to be a chain rule. So 4 cosine theta, that's my power rule, then times the derivative of my inside function, which is negative sine theta. And then for y, let's see if I can I guess I'll organize it this way. So for my y is equal to 3 sine of theta plus sine of 2 theta. So that means that dy d theta is equal to 3 cosine theta, just doing the derivative, and then it's going to be plus, so this is a chain rule, it's going to be cosine of 2 theta times 2 for the inside function. So she put 2 cosine of 2 theta. I'll just copy NILA. I'm sure lots of people have experience doing that. 2 cosine of 2 theta. All right, so then all we have to do is evaluate these two at pi over 2. I was thinking of sort of squinking that in here, but I didn't do it. So I know that dx d theta at pi over 2 is equal to, well, I can sort of work all this stuff out. It's negative 3 sine of pi over 2 minus 4 cosine pi over 2 sine pi over 2. But you can save some work here because cosine of pi over 2 is 0. So this whole term, forget about it. It's just negative. So that means all you have is negative 3. Oh, by the way, what I'm doing here, NILA, is the one thing that I thought would improve yours a little bit, because what NILA did next was she took the dy d theta and the dx d theta, and she wrote dy dx equals this whole expression over this whole expression, and then she plugged in the pi over 2. So, it works, but I thought it was a little bit clearer if we said, once we know what dx d theta is, let's evaluate it at pi over 2 right away, and then it'll be easier to write the fraction. So dy d theta. So that's what I'm doing, NILA. It's a little bit different from yours. Slight improvement on what was a great method. All right, so then here I'm going to have 3 cosine of pi over 2 plus 2 cosine of 2 pi over 2, so it's going to be pi, and that's important because this one ends up 0, this one's negative 1, so I have negative 2. And then I can say that dy dx is evaluated at pi over 2 is just this number over this number. It's negative 2 over negative 3, so it's 2/3. So basically, NILA's great improvement is to get rid of the r variable right away, to simplify in clever ways, and then just get dx d theta and dy d theta. And then she just put them together right away. I said, let's just evaluate them at pi over 2 right away, and then I can just put one over the other, and boom, it's done. So good job.